Hi everybody, my name is Alex Schwartz. I'm the principal investigator of the RF Seismograph. The RF Seismograph is the software running on this computer, which is actually a Raspberry Pi. And what we're doing is we're recording the propagation of 6 different channels, HF channels, and trying to determine how these changes in the individual channels relates to propagations, and how these propagation changes correlate with regular earthquake activity. When we go over here, you can see that the white box is the one that holds the RF seismograph software and is run by Raspberry Pi. And the radio below, the TS590, is the radio that we use to record everything. The 590 is a really good radio. It's rock solid, and it's connected up on the roof to our big vertical antenna. And below we can see our setup, where we're gonna have the PowerPoint presentation that we're gonna be talking about. Welcome to our presentation. Here we have our first image, and it's an image of what we believe the earthquakes do to the ionosphere. They create shock waves while they develop, and this can take a precursor up to several hours before they actually erupt. And the changes in the ionosphere is what causes the changes in propagation that we do record with the RF seismograph. Where is the RF seismograph located in relation to a fault line? So as we record these earthquakes, we're actually quite close to a fault line. There's a fault line just about 5 kilometers here when you see where I put my mouse. This is the Seymour fault line, and we believe at this point that it's possible to see the earthquakes affecting the RF seismograph because of these fault lines. The fault lines are weak points in the crust, and give the magnetic field lines an opportunity to come up easier and affect the ionosphere. And British Columbia, where I'm from, is littered with fault lines, but most of them are quiet and provide maybe just enough of a crack for us to see it as a propagation change. Where is the RF seismograph in relation to the big Pacific fault line? So the RF seismograph is located up here. That's Lynn Valley, and the island in front of us is Vancouver Island, that has quite high mountains. And this is the tip of Washington. And down here we have the Seattle fault lines, which are about 100 kilometers away. And the ones out in the Pacific coming down this way are about 250 kilometers away. And it's interesting to know that we have a lot of ham operator communities that are located along those fault lines. So like if you're looking at Japan, New Zealand, Hawaii, the new west coast of America, Florida, the Caribbean, Italy, Argentina, subconsciously the ham operators already know that earthquakes play a role in propagation. How do earthquakes change propagation? Energy source. The energy source is the tectonic movement of the continents. So we've done some research on find out how the continents, when they collide into each other, how the vibrations can create magnetic field lines. And there's one effect that is probably most prevalent to creating all this energy electric or magnetic energy, and it's called piezoelectricity. And piezoelectricity is a very simple way of creating electricity, and this is whenever you have a crystal or a rock that is sliding and vibrating on top of each other, that will create this kind of electricity. The energy buildup comes out of the ground, or is in the ground as a current, and because the permeability of the air is a lot easier to penetrate for field lines, the fields come out of the ground, and we can see that here. They come out of the ground, and as they shoot up, they start to affect the ionosphere. And as they affect the ionosphere, it creates shock waves. So when you have a 40-meter radio signal that bounces off the E layer and then comes back down to the D layer, you have these shock waves that create areas of thinner attenuation, and then that allows the shortwave radio come through. So this would also explain why you have short windows of 40-meter openings, because these shock waves are quite short and they're quite small. How do earthquakes create electromagnetic fields? The simplest way is, and the most used way of creating electricity, is the piezoelectric effect, the same way it is used in a cigarette lighter. Here we have the principle of a cigarette lighter, and we all used one, and we all have known that this is how this works. It's a very reliable way to create electricity. If you have a chance, there is an interesting talk on YouTube about how the piezoelectric electricity works and how it all connects together, and it goes down to the molecular level of the crystals and explains how it really works, and it's a really interesting effect. The 40-meter propagation by minor quakes. So when we talk about minor quakes, they're below M4.5. And we have an interesting, this is one day, this happened on January 12th this year. This was the propagation that we recorded for all day. We have these presentation reports on our website, on our user group, and we have recorded reports for over a year now. And we just want to point out some of the minor things here. Like you can see, the green quakes are the smaller quakes, the red ones are the larger ones. And we can see here that a whole bunch of small quakes together will create sporadic propagation here on 40 meters and on 20 meters. And as we get over to the stronger quake, which is the M4 5.9 from Japan, you can see that the 40-meter band and all the other bands, all of a sudden it just drops out while the quake develops. And then as another minor quake comes up, 40-meter comes back up for another 45 minutes, and then it dies down again. And then it's kind of a back and forth play of this. Like all day there was not a lot of propagation available on all bands. But again, we have the attenuation here when we have the Baleine Island region earthquake. And then after, when you see the green dot with a green spike, which is a local minor quake, all of a sudden we have more 40-meter propagation. And this continues on, and then have the 5.0 quake. And here we have the propagation, the attenuation with the 5.0 quake. And then as the local minor quakes take over, 40 meters opens up again. And here we can also see the 80-meter band opening up as the quakes develop. And here we have the 5.9 from Indonesia, and we can see that it has actually quite a long precursor, starting here at 1600 UTC, going all the way past almost to 2000 hours, and attenuating everything. The 20 meter band comes up because again we have a minor quake that changes the propagation, and again a medium-sized quake here, the yellow with the white spike, again the band changes, and this back and forth again, band changes as the quakes release for the day. Why is the ion region not on the surface of the planet? So this brings up a very interesting concept, that if you have constant earthquakes happening on the planet, there is a distinct possibility that they have something to do with how far the ionosphere is away from the planet. And the idea here is that we have all these quakes that occur on the day side of the planet, and while we have the ionosphere, which is this bulge here, getting radiated with the solar wind, and we can see that the ionosphere is moving in, and that the force that's counteracting the ionosphere, keeping it away from the planet, are the earthquakes. When we go to the night side of the planet, we can see the ionosphere is further away because it gets pushed out by the energy of the quakes. So this brings up a very interesting proposition, that if the ionosphere is getting moved out by the quakes, that will explain why the 40 meter band goes wide at nighttime, and why we have such changes, because when you have daylight, the ionosphere is very close to the ground, and which would make not provide a lot of skip, and would also not provide a very good angle to get a signal to a DX location. But on the other hand, when we're on the night side, where the earthquake's energy can actually push out the ionosphere more away from the planet, the DX position, DX signal propagation is much better. And so this brings us to the Mars, because the reason why we want to look at Mars, we want to see what's different on Mars. And one of the things that's different on Mars is the fact that Mars doesn't have or has a very limited amount of plate tectonics. So we are this picture that we're looking at is the MAVEN ionosgraph that was taken sometime in 2015, I believe, and we got this off the off a website, and it's quite interesting. So according to the MAVEN measurements, actually there is an ionosphere on Mars that is capable to propagate shortwave radio propagation. So there is this link if you want to look at it in more detail. But the interesting part is that there's also ozone found on Mars, which is kind of I find that interesting, because there is ozone. That would mean that there's oxygen somewhere in the atmosphere that can turn into ozone, and they also have recorded from the planet that there was aurora, which also would hint that has something to do with how well the ionosphere works on Mars. The difference between Mars and the Earth is the way we have the Earth has a big moon, and the big moon drives most of the plate tectonics, and plate tectonics drive the electromagnetic fields that are coming out of the ground that are creating a lot of the propagation that we see when the sun is not active. So what would happen is all the additional energy that that the plates create have a lot of effect on the ionosphere, and that provides us with the propagation that we see. The propagation that we see, that we can actually measure, has short periods, like 50 minutes there, 1 hour there, 45 minutes, and it's never longer. So the propagation is not from the sun, because the sun's too far away to provide these kind of short intervals of propagation. And also, as we've seen earlier, the intervals of the propagation align with medium-sized and the small quakes that are recorded by the USGS. So this brings us to the last point on this slide, is during pole reversal, will we be able to survive in the magnetic bubbles that are created by the tectonic plates? So we'll see when that comes up. And here we have something that we're organizing. We're organizing an X-style prize as a competition for recording earthquakes via the shortwave radio. So we understand that there's a lot of hesitation and a lot of reluctance to accept the fact that earthquakes create propagation. And what we want to do is we want to create an X prize, depending how much money we collected. But it's going to go to the university that can first build and prove that build an RF seismograph and prove that the RF seismograph is actually working and detecting earthquakes. And that's our X prize. And if you go to our website, there's a link if you want to donate to our X prize. We appreciate anything you can give to get this forward. We are thinking that we might collect up to $20,000 on this, and that will be an incentive to get university thinking to start monitoring our frequencies for propagation and the earthquake signals that we at the moment we're the only place on Earth able to detect the earthquake changes of propagation. Since we're limited to 20 minutes per show, we have a much more detailed description of the whole project, which is continued by the presentation that we unfortunately don't have enough time to show. But there's a whole bunch of different interesting subjects that you could go and find out more about, and we also have interesting links on more detailed studies on how the RF seismograph works and how it all fits together with our science. Here we see the antenna that we set up. This is more detailed information. This shows the information about the RF seismograph itself, how we built it. There's another portable version of the RF seismograph. It's all based on the Pi. This is the board, the converter board that is needed to make the radio possible to be read into a sound card by the RFB board. There's some references, more references, and we're getting to the point where we have questions, and we want to thank everybody. If you're interested in building an RF seismograph, if you work for a university and you want to start this as a project, we have kits are available from our website. The instructions are also available from our website, from our user group, and email me, and we'll make everything possible to set you up with an RF seismograph so that you can start monitor and test for earthquakes wherever you want to be.